Hello everyone. So, this is going to be our last problem in the modular arithmetic unit. Let's take a look at it. So, let n be a positive integer. Find the modulo for residue of n given that 7 to the nth power is equivalent to 1 mod 10. Alright, well, it's kind of strange they brought up modulo 4 residue of n. I mean, clearly, when we have a situation like this, well, we should just check out exponents of 7, starting, I guess, with 7 to the 0th power, which is just 1. So it would be 1 mod 10. And therefore, so we would have this situation where n is congruent to 0 mod 4, since it wants us to state the modulo 4 residue. But let's just find some more examples, because in part B, it's asking us to find the unit digit of 7 to the 7th to the 7th power. Now, this is quite a big value, 7 to the 7th to the 7th power. And sometimes people will claim that it's the same thing as 7 to the 7th to the 7th. Now, this is not true. This is not true. Because this becomes 7 to the 49th power. What this becomes is 7, well, to the 7 to the 7th power. And 7 to the 7th power is actually just quite a big number. It's like 8. It's like 8 like freaking million something. So yeah, it's an incredibly large value. So don't make that mistake. It's a number that's just, it's like, this thing is just going to be a number that's incomprehensibly big. So we have to find a way to simplify it. And whenever you have these stacked exponents, you always organize it from the top down. So like you would find 7 to the 7th, and then raise this 7 to whatever that number was equal to, that like 8 million something whatever power. So, is there some sort of link with modulo 4 and 7 to the whatever power? Let's find out. Well, if n is congruent to 1 mod 4, then we would get that 7 to the nth power. I'm going to change these to the nth power because we're going to try to generalize this a bit. Because n doesn't have to be 1, it could be, in this case, 5. That would be, well, 7 to the first power is 7, which has a unit. Oh, by the way, unit digit means like 2. That has a unit digit of 2. It's whatever's in the ones place, basically. So we want to find what's in the ones place of 7 to the 7 to the 7th power. So 7 to the first power would be 7 mod 10. Then going to, like, if I said that n was congruent to 3 mod 4. That would be the same as, well, 7 to the 3rd power. I mean, no, whoa, I skipped one. 7 to the 2nd mod 2. That would be equivalent to 49, which mod 10 is just 9. The reason we're utilizing mod 10 is because that is what will hand us over that ones digit, that unit digit place. Since mod 10 is going to take away everything except for the remainder after division with 10. So all you're left with, the remainder in this case being your units digit. Now, then we have n equals 3 mod 4. Well, that is going to get us, 7 to the 3rd power. So 7 to the 3rd power is 343. So the mod 10 in this case, 10 divides evenly with 340, you would have a remainder of 3. And mod 10. Now, since we're in mod 4, well, the mod 4 would repeat itself, but how do I know that it's directly going to correspond with the powers of 7? Well, like, for instance, if we continue to take 7 to the 4th power, that becomes 2,401, which is equivalent to 1 mod 10. Okay. So, how about 7 to the 5th power? That's equivalent to 16,807, which is equivalent to 7 mod 10. So as you see, it goes 1793, 1793. So it seems like it's going to keep repeating itself, certainly. So we can safely assume that every, every 4th term, it's going to just cycle back into ones place. So, what can we do with this information? Well, again, when we're evaluating 7 to the 7 to the 7th power, we want to take that piece first. Evaluate that piece of the puzzle. So, for instance, now I want to find something about 7 to the 7th power. But this is an exponent. So, in terms of the exponents, I'm going to evaluate it in terms of mod 4. Now, because that's the case, we are going to get that 7 to the 7th power. Well, 7 mod 4 is equivalent to, well, I like to work with like values like 1 or whatever. So like 7 mod 4 is technically 3. But you could also think of 3 as -1 mod 4. And we've done some examples of those negatives in the past. So I'm not going to dwell on it for too long, but this would become -1 to the 7th power, which, since it's an odd exponent, would become -1, which we know is equivalent to 3 mod 4. Now, alright, that's interesting. So, using this information, I know that 7 to the 7 to the 7th power is going to be equivalent to 7 to the 3rd. And if n is equal to 3 on my exponent chain, then that's going to just become equivalent to 3 mod 10. And so we would say that that 7 to the 7 to the 7th has a unit digit of 3 based on that process of repeating exponents. And that is it, the last problem of the modular arithmetic unit.